to the real universe soon. Oh, look at this. Good heavens. How did that, it's over there. Well, just to confuse matters, I've got half of my talk on a keynotes slide and half on a beamer. So I'm not sure which half is on this. I have a list here and I have to flip from one to the other as I go. You can see I'm really well organised. That's another thing I learned. Be organised. Okay, how do I do this? Okay. Having got over this bit of propaganda for not believing your professors, well, I might as well finish. At the moment, we have some marvellous theories of the universe. We've got inflation, we've got dark matter, and we've got the explosion at the beginning. What is it? Inflation. Now, the evidence for inflation is pretty much non-existent. It's just wishful, in my opinion, it's wishful thinking. You draw a curve, define a potential, and hope that's how things happen. The reason I say it's wishful thinking is we can't actually see back then, and I believe as a mathematician that physicists should only believe what they can see, not what they wish for. Okay, so I lost a third of my famous audience there. Then there's dark matter. Well, we know that with galaxies, the stars should be flying away because there isn't enough mass in the center of the galaxies to hold them together. Now, they do hold together, and so there has to be either a problem with general relativity, which is always a possibility. Perhaps it's only a good theory for the solar system and small regions and not for big. The other possibility, which is a pretty good thought, is that there's dark matter. There's something that we can't see out there, but nevertheless we can observe it by seeing it bends light rays and it holds galaxies together. So that's one of the great theories. The third theory is inflation. Now, Nobel Prizes were given for inflation not too long ago. People said, oh, the universe is not only expanding, it's accelerating. Well, there's been a lot of observational work recently which is casting a doubt on that. Because if you're going to measure the rate at which the universe expands, then you have to have some way of measuring how far galaxies are away from us. And that means standard candles. And that means somehow you've got to have somebody in a distant galaxy flashing a torch and saying, now this is a torch of this strength. If you watch how much it redshifts and watch the brightness, you should be able to tell where the galaxy is. Now, the standard candles, aren't quite as standard as we hoped. And so, particularly type 1a supernova, that means that now we're getting lots of papers coming out saying, well, it's instead of being at the 6 sigma level, it's at the 1 sigma level, or even worse. And so, good. For all you students, this is great. You do not want to come into physics at the point where everybody knows everything and all you can do is clean the desk and the floor for your professor and possibly get some coffee. You can have your own ideas and you can be part of the revolution which in 10 years' time comes out with a whole new theory of the universe, which in 100 years' time may be totally wrong, but that's another story. Okay, I better get on to what I was going to talk about. I haven't got much time left. Okay. what I'm going to talk about is black holes and the electromagnetic fields around them. Now, the first black hole solution, in fact, the first physical solution of Einstein's equations was Schwarzschild. And it was very simple. Einstein was amazed because he didn't think anybody would ever solve his equations, and Schwarzschild came up with this. You'll see there's a 1 over 2, well, there's a 2m minus r in a denominator there, one or the other. And that means that at some point, one of those coefficients is infinite. Now, for a few years, this came out in 1916, and it wasn't until after 1920 that Schwarzschild showed, Eddington showed here that you could change the coordinates. In the original coordinates, people thought that at r equals 2m, the event horizon, they thought that this was a terrible place and that the curvature was infinite and all sorts of things they thought were happening there. Eddington showed it wasn't true. He put it in this coordinate system. Gee, I mean, it could hardly be simpler than that. There's a 1 over r term, so when r is equal to 0 at the origin, there is a true singularity here. The curvature gets stronger and stronger as you approach the origin. And that shows nothing much was happening at the event horizon, except that if you went through it, you couldn't come back. So that isn't good. But now, the form of this here, it's not the form in capacity space, that's space of special relativity, plus some multiplicative factor times the square of a null vector. That vector is actually a light-like ray. So there's a whole lot of light-like directions coming out of the center, pointing out to infinity, straight lines, geodesics. And so the method is extremely simple. It also turns out that every black hole has that form. Okay. Now I'll explain perhaps later. On the other hand, I may not explain. It depends. Okay, let's see if I click this. Yeah. No. I think I have to change at this point. Have I got my other file? Probably not. They didn't even know what it was.
Should they change to the other side?
Yeah. Just as well. Ah, yes. Thanks. Just stick around because we're going to change back and forth. Okay. Now, the trouble with this black hole is a completely round body collapsing down with no spin, because everything spins. We're all spinning now. We may not very much, but you know, there's motion. So they thought perhaps when the body's spinning, you won't get a singularity at the center and everything will be nice. Okay, so for about 40 years, people looked for a solution which was for a spinning black hole. For any spinning black hole, there wasn't any even cricket ball spinning. There was nothing for that. So I got fortunate to find the Kerr metric back in about 63. I'm not going to say where it came from. It came from completely the wrong way of looking for it. Okay, at the time, people were looking at the Riemann tensor and looking for special directions and what they call principal null directions, looking for repeated roots of eigenvectors and eigenvalues. And they're also just trying to find any solution of the Einstein equations, which was independent of time, because you want to have a body that just isn't changing, and which was independent of a direction, like spinning a milk bottle around the major axis. So this, that is in effect reduced the field equations from 4 independent variables to 2. Unfortunately, although the equations were put in many beautiful forms, they were never solved. So I came at it in completely the wrong way and eventually found this solution here. Now, this does show. Yeah. It's of the form ds naught squared, which is this rather complicated looking expression, plus a constant, a function times the square of a vector. That's what that means. Now, I happen to know that this part here, this first part, from there to there, was flat space, was Minkowskian. That was because I knew its curvature was 0, actually. And so all I had to do was find a coordinate transformation, and that's what it is here, which produced this form, flat space plus something squared times coefficient. Very much like force field, except it's got another parameter. This would have 2 parameters. I might say I started with a lot more parameters, but they were all non-physical. And at the end of quite a lot of work by myself and a lot by other people who was also trying to solve similar problems, all I had left was one lousy solution with 2 parameters. Okay. So, what happened there? So, the question was, if I looked at a large distance away from it, we could see that pretty much it was like source field, okay, but it was not quite source field. So one day I went to my office with the head of the institute I was at, Alfred Schultz. I said to him before I went, I'm going to calculate its angular momentum. So Alfred said, good, I'm coming too. So he came into my office and we calculated it. Now, all I did was I took this metric I had and I expanded it in powers of the distance from the origin. Okay. And the leading term was Eddington's term for the mass, and this was the next term, the 1 over r squared term, in effect. Okay, so, and then because I'd worked with angular momentum in approximation theories, I knew that all I had to do was figure out an infinitesimal transformation to put it into a form where I could see what the angular momentum was. I did that, and I turned to Alfred and I said, it's rotating. So he was even more excited than I was, but that was because he knew people had been looking for it for 40 years. I didn't know anything about that. So that was the Kerr solution. That's a rotating body, mass and angular momentum. Okay, with any luck, the next, oh yes. Now, I'm probably on the middle. Okay. The coordinates I had, oh, yeah, I think we missed this one out on the way through. That was the original, no. Yes, I've got it to the, I did have that up. I've got it to the Kerr-Schultz form. Now, it was still a bit complicated, and the Boyer-Lindquist form for the metric was got by taking that system and doing, not in the Kerr form, but in the original form, and doing a slight coordinate transformation to get rid of some of the components. So that produced this metric here, which is the way that most people see the form. Okay. Now, actually, soon after I found the Kerr metric, Ray Sachs and I tried to find an interior solution. Nobody's ever found an interior solution but we tried. And we worked solidly for at least 30 minutes. And first we put the metric into that form because it's only a 10 minutes at the most job, because it's just linear algebra. Take a matrix, do a linear transformation on it, which is what that blue stuff is, and you'll get the answer. This form has got singularities all over the place. When you approach the event horizon, it's singular. So just like Schwarzschild, that's got the same problems. Now, the beauty of that coordinate system is you can solve equations in it easily. Well, that's fine, solve your equation. But what happens at the singularity, at the event horizon, may not be as true as you think it is. And the trouble is it's boundary conditions. You know, if you're going to solve some equations and you have a boundary, in this case, a singular boundary at the event horizon, then you've got to have boundary conditions. But boundary conditions on a singular horizon are a bit difficult to specify. So there's a lot of troubles have occurred there. Anyway, Kerr metric, yes. Forget all that. This is a diagram that a friend of mine did for me. The Kerr metric's got an event horizon, that's the big sphere. If you go inside the big sphere, there's no way you can avoid falling to the next sphere. Once you get inside there, you don't have to complete. You don't have to continue falling. The null cones don't all point inwards there. Nobody knows what happens on the inside. If there's no matter, and you think of this as just a solution like Schwarzschild, which came from nowhere with no matter, then there is a singular ring, which is actually a branch ring. Just like a branch point for root z, that's a branch point for a square root function. The spherical polar coordinate, actually. If there was no matter, you could go through that ring into another universe where the mass is negative instead of positive. You could then come back through the ring into your own universe. But that's all complete nonsense, because the only way of getting a black hole is to form it from a collapsing body. So we presume that inside there is whatever happened to the 10 to the 7 solar mass object that collapsed into it. There is a theorem that says there has to be a singularity inside somewhere. Now, you've got to take that with a grain of salt, because nobody proved the theorem they wanted to prove. What that was proved by Roger Penrose was that somewhere inside there, this is fallen off. Somewhere inside there, a light ray has to have finite length, can't go to infinity. Well, you know, what does that mean? Also, he has to assume a very strong condition on the matter. Now, clearly, we don't know what happens when you compress matter to some arbitrarily high value. So we don't know what the physics is inside. What I believe we can say, though, is that the body is spread throughout that inner surface. I know there's going to be matter all the way down that red line, that central line, because you're never going to form another universe suddenly. Pop, here's space is suddenly expanded to include this whole new universe. So, and anyway, rotation is not going to throw you off the central axis. So I think that it's probably not as complicated as we think. Okay, oh God. Can I get my other one back? Okay. I don't need any diagrams. We won't, because I'm running out of time. My friend's taking over. What happens if it's charged? Well, this Kerr-Schill stuff, having found that this metric was of the what's called the Kerr-Schill form, I looked for all metrics of a similar type within the field of algebraically special spaces I was looking at, and I found that, as well as the one I already had, there was a whole, I could generalize it by introducing an arbitrary function of a complex variable. The trouble is, they weren't singular at infinity, so they weren't physical. Okay, I went to a party at Alfred Schill's, and he and a friend, Jerry Plavansky, were talking about solutions of that type. And I said, oh, I might know some, but I'd calculated them one morning, and I didn't check it, so I didn't know. Anyway, Alfred and I went into his office and proved that any metric of the type flat space plus the square of a null vector had to be of the sort of metric that I already knew. And it turned out that was everything. And we actually proved that in his office at the party, which was amazing because we'd already been drinking for at least 3 hours, I suppose. Okay, what happens if they're charged? Charged black holes are exactly the same type. But it gets more interesting because for the charged black holes, you can take the Kerr metric and add a charge to it. And that will be like a charged Schwarzschild, Riesen and Nordstrom, except it's spinning. Okay, that's pretty unique. All it seems to have is an electric charge. However, when you look at these Kerr-Schill metrics, there's more than that. It includes a solution which is basically, I should have said, everything's linear here. You keep adding bits together. You add the electromagnetic field onto the gravitational field, everything adds. This is linear mathematics. So it turned out you could add onto this charged sphere a singular electromagnetic field shooting out from inside the so-called horizon. In other words, in this solution, the horizon isn't a full horizon. So there's a problem here for any graduate student that wants to look at this, is calculate the field. Actually, I've got it, but in lousy coordinates, and see whether it corresponds to not a black hole, but a very collapsed object with a jet. And we see these in the sky, so it would be of interest if it was. Well, look, I've got to stop now because I'm already 3 minutes over, and my brain is totally used up. I know nothing else. So I'll leave you with this last thought. Don't believe everything you're told, especially by me, and good luck to you all. You know, you really are in a situation where we don't understand quantum mechanics, we sure as hell don't understand the start of the universe, the end of the universe, or anything else. So we don't even know how to get damn things up on the screen. Okay, I'm finished. Thank you. Yes. Questions?
So I would like to ask what in your eyes would be the best experimental verification of the Kerr black hole?
Well, actually, things are looking up for experimental verification of whether these objects we think are black holes, like the 4 million solar mass concentration of matter at the center of our galaxy, Sagittarius A star. We're hoping in the very near future to get pictures of black holes. So you can't actually picture the black hole, but you can picture the lack of anything that you can see, or you can at least see what's happening in the center. So we'll be able to picture what's happening, and we'll be able to tell whether it's spinning. Anyway, that's likely to happen. The LIGO may observe something, gravitational radiation. They haven't really got the templates yet that will fit what was observed. This, but clearly they're almost certainly seeing two black holes coalescing. Two rather large 30 solar mass black holes. But until you can actually see it, and I mean, take a picture of it. Looking at some wiggles on a couple of charts, all that says is something happens, and your theory is it's a black hole, a black hole. We don't really know because we can't see. Okay.
Okay, if there aren't any more questions, then thank Roy again. Yeah, let's try this, and if not, I have yes.
Well, I will try to show.
I think should be here. Is it a PDF file?
Yeah, please. No, I just go through. Well, it's okay? It's okay? Yes, it's there.
Oh,
Okay?
but we need to put it in a full screen.
Oh, I don't know how to do that. You know how to do it?
Maybe second.
Go on.
Any experts on Mac would be appreciated. Yes.
How to go full screen?
You?
No.
Enter.
No. Oh, yes, you're right. Okay.
Okay, so it's a pleasure to have two very distinguished guests today. So we just heard Roy Kerr talking about the Kerr metric, so it was great. And our second speaker today is Kerr and Ruffini, the head of the International Center for Relativistic Astrophysics in Rome. And he will tell us about gamma ray bursts.
Well, it has been a long time since we were working with Stephen on the first step of the physics of the black hole. and everything started for my side in working with John Wheeler on the Kerr solution, and especially on the process of possible extraction of rotational energy, which had been introduced by Roger Penrose and look better in that structure. We were at the time in Princeton, and there were many bright students with us. And one of them, of course, was Dimitris Christodoulou, and we worked very much about the mass formula of the black hole. And it's interesting that this work really, as you can see, started continue from the 70s on for one very, very intense set of contributions, which were practically timed in from September 1770 to March 71 to March 11 to October 15, 71, and finally this beautiful formula of the black hole mass energy was obtained. We had exchange at the Texas meeting and in other places with Stephen, and in particular the most interesting part, which still today we are working on, is the fact that the characteristic properties of this formula is the reducible mass. And to me, the fact that the reducible mass is independent on the charge and on the angular momentum itself is still an argument of research, and I understand from the work that Perry just showed me today, there are some analogies with our thinking. Therefore, this field is still very open. And of course, one very important moment, thanks to the work of Riccardo Giacconi, was the identification of the first black hole in our galaxy in Cygnus X1, and understanding the role of the critical mass. A neutron star can exist up to a critical mass which Oppenheimer estimated 0.7. We have been working, at the time Cygnus X1 was discovered, the mass of the black hole not pulsating was larger than 3.2 solar masses, and they were important results. This is history. I would like to jump now to the latest result, which have been exposing to Stephen in the last 2 days. And the jump is to the latest result, what we have learned from the 70s and Cygnus X1 all the way to today. I will just give a summary about the key point. I mean, of course, the instrumentation jumped enormously, because we went from the Vela satellite to the Compton satellite to the satellite of Fermi and Chandra satellites, and especially to the Bepo-Sachs satellite, which allowed to identify for the first time a gamma ray burst. And gamma ray bursts, they are short, long, they are isotropically distributed in the universe, and we have gained an enormous information, especially the characteristic energy of this system is up to 10 to the 54 erg. But differently from the previous, all the previous work on a single system like Cygnus X1, what has been developing, especially in the last 2 or 3 years, is to understand that objects like Cygnus X1 are just a special moment of a much more complex evolutionary scenario, which is much richer and start or Sen X3 or Cygnus X1 are just a moment in an evolutionary scenario which is much bigger and richer. You can start, in general, from very massive star, 30 and 60 solar mass object, like Eta Carinae, and the more massive object can evolve first, creating a black hole, and with a companion star, like Cygnus X1. But there are other possibilities in which the most massive star evolve in a supernova, accreting, like in Sen X3. And by far the most interesting case is this one of Sen X3, because the neutron star, this companion star, can evolve itself in a supernova, and then you have a supernova close to a neutron star. And this I will show, and of this spatial evolution, of which this star going in a CO core, evolving in accretion in a neutron star, I give you in a moment a few examples. But also this other system of a black hole plus a CO core which can explode in a supernova can give rise to a black hole neutron star system. And from this neutron star merger, you can form a black hole. But the most interesting one are this one, in which you have a neutron star with a supernova companion. And we understand now quite a lot of this dynamic, I will show you in a moment. But the byproduct of this GRB emitted in this case, or in this explosion, is a binary neutron star coming from the supernova and from the neutron star companion, which has not undergone gravitational collapse. And this system generates a binary neutron star. And binary neutron star can evolve themselves, again, if the mass is larger than the critical mass, to a more massive neutron star, emitting a short gamma ray flash, or if the mass is larger than the critical mass in a GRB and forming a black hole. This other system instead, where you have, this is the case which we will see in a moment, in which the supernova accreting into the neutron star form a black hole, and therefore you end up in a black hole neutron star binary, again, which can evolve later on in a black hole. And each one of these can emit a gamma ray flash. Therefore, contrary to what people thought, some people still think that there is one GRB. They are GRBs of many different shape, intensity, characteristic, and they are part of a common evolutionary scenario. But only two of these form black holes. Again, we like to think about this phenomena like a cosmic matrix. This also is the one of the most fundamental differences introduced by gamma ray burst. Usually people look in the sky for a single system, like the crab, or a single system. And here we are talking about a complex system which starts from a supernova and a neutron star binary. It merges, it forms a black hole, and from the supernova a new neutron star. Therefore, you have kind of an S matrix, like in particle physics, in which a plus and minus go in a plus and minus, or a neutron star plus a supernova core evolve in a new neutron star and in a black hole. In particle physics, you have the characteristic transition of 10⁻23 seconds determined by Fermi interaction. In GRB, you have phenomena lasting of the order of 100 seconds, we will see in a moment. But the in-state and out-state idea is the same. Of course, there is a huge difference conceptually that while all the particle physics in this process are reversible, in the case of a neutron star and a supernova, in 100 seconds you form a new neutron star black hole, but the system, this matrix, is not reversible. Okay, I would like just to summarize quickly 4 different results which we have obtained in the last few days, and shortly illustrate them one by one. The first topic is on the induced gravitational collapse scenario on gamma ray burst. I have been presenting the idea that a supernova explodes in presence of a neutron star companion at a distance of the order of 10 to the 10 centimeter. The accretion of a supernova on such a neutron star is completely different from the accretion process that we have been knowing in binary X-ray sources, for example. Just to give a number, the accretion rate of the supernova of the neutron star is of the order of 1 solar mass a second. And completely new physics has to be considered. Was introduced by Zedovich with Wilson, and is practically based on the Bromley-Hoyle radius, and the characteristic structure of this system is the emission of neutrino and antineutrino, which allow the cooling of the system and the formation of the black hole if the neutron star goes over the critical mass. And these are some of the most beautiful examples obtained in our group by Lara Becerra and by Fryer, collaborating with us, doing the analytic work in Rome and then doing the highly sophisticated work from the supercomputer at Los Alamos. Here you have the supernova here at the moment of explosion, at the time t equals 0, and the neutron star in a binary around. The binary period is of the order of 4 minutes. And then after this you just have the supernova exploding. Okay, this is timed 3.8 seconds after the supernova explosion. This is 7.7 seconds after the supernova explosion, when the supernova expansion has already engulfed the orbit of the neutron star. Being a 4 minutes period, you see that already the neutron star has moved a little bit upward, and the shape of the supernova has been affected. This diagram is at 254 seconds after the explosion of the supernova. The accretion on the new neutron star, on the companion neutron star, has created a cavity, the one you have seen before in the treatment of hypercritical accretion. And from the supernova, you have a new neutron star which has been formed. And finally, when the critical mass is reached, which is after 254 seconds, this is the moment of accretion leading from the neutron star to the black hole, the GRB is emitted, and there is the expansion of the GRB, both at infinity and impacting on the supernova ejector. This is this characteristic system which we call binary-driven hypernova. And there are many of these examples. There are of the order of 700 binary-driven hypernova of this kind. But I would like to call your attention on a phenomena which happens just at the beginning, and then I will return to that, of the GRB emission, the J emission, which keeps going after, but is just originating at the time in which the black hole is born. I will show you this. Okay, the second topic is related to the previous one. It's about the emission of flares, which the first one after the prompt radiation of the GRB, Bepo-Sachs observed a flare, and it was a big mystery what this flare represented and what this plateau represented and this late phase evolution represented. But we have studied now a large number of these flares with great accuracy, and I just indicate you the paper in 2017. But what is more important at this stage is to understand the system that we are speaking. The system of this GRB with a supernova and a neutron star, of course, are binaries. They are not single object like they have been considered up to now gamma ray burst. The popular, very popular version is that you have just a accretion disk on an already formed black hole which emit jets. And in this case, you don't have a single object and a black hole given. You have a supernova starting in a binary. Here is the supernova, and here is the neutron star companion, which we have idealized, the accretion star, and here you form the black hole, and which is this condition here. You have the supernova emitted, the accretion of the neutron star, and the formation of the black hole. And it's like a Chinese cooking, one of these fortune cooking, where you have the supernova, this cavity, and in the region in which the density of matter is very much smaller, you have the GRB coming out in this direction. I don't want to be too technical, I want just to give you a general idea. Here you have the black hole formation, the electron-positron plasma emitting, the baryon loading is of the order of 10⁻², the Lorentz gamma factor is up to 1,000. But another part of the GRB impact cannot go to infinity in the low density regime, but impact on the jet of the supernova. And this is the part of the jet of the supernova which, once you do all the computation, you reach, it moves at gamma less than 4, very low velocity, and not high velocity like the one of the GRB at infinity. And this is the one which we see in the flare. Okay, this is the second topic. Now, of course, this is the case of the supernova interacting with the neutron star. There are other GRB which originate from two neutron stars in a binary system. And this is, again, a very, you see the time scale of the phenomena, the short GRB, and then just after a few seconds, a few fraction of a second, 0.01 second, you see the emission of the ultra high of the jet radiation from Fermi, and this again on. I don't want to say. I hope to be able to transmit this concept, which is if you look at this jet radiation, which is originates both at the it originates both in short GRB and in long GRBs, and the slope of this jet radiation is practically the same in the two cases. It happens, and the time of the turn on of the jet radiation is here at a fraction of a millisecond, and here again in the long gamma ray burst where the system is much larger, around from 10 seconds. But it keeps going with this power law behavior. And in our opinion, this radiation is just the moment of formation of the black hole, both in short gamma ray burst and long gamma ray burst. In other words, I don't have too much time, but just to give you an idea, there are binaries, both binary of neutron star or binaries from a supernova and a neutron star. But in both cases you have accretion. In the case of a binary neutron star, you can reach the critical mass or not. If you don't reach the critical mass, you form just a larger neutron star. If you reach the critical mass, you form the black hole, and only in this system, which form a black hole, you see appearing the jet radiation. And it just, therefore, what we are seeing is not that there is before a black hole and before the merging of the neutron star. It's only after the merging of the neutron star that the critical mass is reached, the black hole is formed, and the activity of the black holes is just the jet radiation. The same thing happens in the long GRBs. Therefore, there is a specific signature. In both cases, you start from binaries where no black hole exists in the beginning, and only if the critical mass is reached, you have the jet radiation and corresponding to this emission. There are 7 different families of GRBs. Either you have a supernova and a neutron star companion, then if you reach the critical mass, you form what we call a binary-driven hypernova. In the other direction, you have an X-ray flash. This X-ray flash can form 2 neutron stars, and these 2 neutron stars later on can form themselves an accretion, a short gamma ray flash, if the neutron star critical mass is not reached, a short GRB if you reach the critical mass. Therefore, it's a very complex and rich system. And from this system you can have a supernova in a black hole, and again, after evolution, can evolve in a neutron star black hole system, which itself can give rise to an ultra-short gamma ray burst. In addition, from this short gamma ray flash, you can form another system like a neutron star white dwarf, which accretes to each other and don't form gamma ray burst, but a different kind of gamma ray burst from the previous one. And altogether, therefore, instead of having one black hole just originating from one black hole originating with the disk and the jet, practically there is no jet in none of these systems. They are all binaries, and they have all their characteristic signature which are observed. Lately, Stephen asked me, what about this, all this binary system? Can they be detected from LIGO? And it's not possible to detect them because the characteristic frequency of this binary neutron star or binary supernova neutron star happens at a frequency and an intensity much a frequency which is not very well tuned with the LIGO detector. And the same one for LISA. This shows specific sources of the battery which we have examined in their evolution with correspondence to LIGO and to LISA. And the next slide shows some very recent work that we have just put on AstroPH today. It again works on particles in a Kerr solution, and we have been discussing on this topic with Roy Kerr in Pescara quite a lot. And it's very interesting that even in this problem of a test particle moving into Kerr, there is a difference between our detailed analysis and other analysis in the literature. The fact that the Kerr solution is really completely different behavior when you reach the region up to the last stable orbit, last circular orbit, the way we call with Johnny Wheeler. The fact that the last stable orbit in Kerr has a potential which is approaching the horizon practically horizontally, instead in the Schwarzschild to drop very drastically. And this means a beautiful result from the point of view of these trajectories. That, let me just give you this result, which to me is taking a lot of passion in these days. Namely, you can have a particle falling into Schwarzschild black hole or into a Kerr black hole starting at infinity with zero or injected energy, starting at infinity. All these particles give rise to a burst with a characteristic precursor, burst, and then you take it. Well known. But the Kerr solution in the trajectory has a smooth behavior at the horizon. Therefore, it has a signature. It has a very definite signature that you smoothly approach the horizon without any extra. This is a very clean test. In other words, when you have accretion into a Kerr solution, if you start from infinity, no matter Kerr or Schwarzschild, you always have a burst. But if you start from a finite radii, from a spherical orbit, you cannot have a burst. You must have a clean merge. And we are finishing some work in this direction, because this is a very definite signature. We could have spiraling, yes, but if you have a Kerr metric, theoretically you expect that the spiraling smoothly stop. You don't have anything else. This is a theoretical signature which should be imprinted in the data. Therefore, these are the 4 topics we are very, very active in this period at ICRANet, and I hope very much that you will visit us in Pescara, in Rio, in Nice, in Yerevan, and in the other center. And of course, we will be very honored to have a visit also of all of you, but especially of Stephen. The city of Pescara, where is our headquarters, has given the honorary citizenship to Roy, who is participating with us in this direction, and we will be very happy to have also in the future Stephen visiting us.
This last statement that you made, that it's always smooth in the Kerr metric, does that mean that even if I put in epsilon of angular momentum into the Kerr metric, that I still get a smooth transition?
No.
You mean a limiting curve?
Well, let's put it that way. If you have, we do that for test particle into a given Kerr. But if you have a binary system, not just a test particle, and they are merging, you will reach the Kerr metric always from the top, not by accretion. This is the key point. If you have two massive stars with comparable mass, then you reach always the black hole from the top, with always A over M of the order of 1. Therefore, Therefore, this is the reason why we study A over M of the order of 1. Because it's a nice problem, clean, but astrophysically, if you have two comparable mass, you end up always with A over M, not necessarily 1, 0.7, 0.8, but this is sufficient to have this phenomenon. Is that clear?
Any further questions? If not, let's thank Remo again. Please join us for a coffee and tea upstairs.